All right, we are supposed to consider all lines in the xy plane that pass through both the origin and a point xy on the graph of y equals x squared minus x plus 16, specifically on the closed interval from 1 to 8. We're looking to figure out which line has the minimum slope. All of these things are talking about slopes, and we're looking for the minimum on a closed interval. So I want to think to myself, I'm going to have an x value, and then I'm going to have a slope value, and I know that I need to consider what's happening at the endpoints because of that closed interval. Okay, great. If I want to minimize the slope, I should probably find the slope. I know from previous classes the slope could be written as f of b minus f of a over b minus a, or maybe we do y minus y over x minus x, where this is one function and this is another function, right? So I got to think about what are my 2 points that I'm trying to connect. I'm trying to connect the origin. So one of my points is the origin 0, 0. The other point I'm trying to connect is the point x, y. So I want to find the slope between those 2 points, and I want to find the minimum slope. So this will be my primary equation that ultimately gets the calculus. So right now, I have the fact that my slope is equal to y over x, which is great, except my slope is currently depending on 2 variables. So I need to use a helper equation to help me replace one of those variables. In this case, I'm going to choose to replace y just because it's a much easier equation. We already have what y is equal to, as opposed to trying to solve that quadratic and go from there. So I sub that in for my y value, and now I have a slope. What am I supposed to do with that slope? I'm supposed to find the minimum. Okay, well, I could take a derivative using a quotient rule, but I'm going to do a little bit of algebra first. If we do x squared divided by x, we're left with just x. Negative x divided by x is negative 1. 16 divided by x is going to be 16x to the negative first. Now I can do calculus. M prime is going to be equal to 1 plus 0 minus 16x to the negative second. From here then, I need to work to find my critical numbers. I'm going to look at where the derivative is equal to 0. And I'm writing this like this just so we get a better image of what's happening. I also need to consider where is this undefined. Well, 1 minus 16 over x squared will be undefined when x equals 0 because we cannot divide by 0. Luckily for us, though, I was only supposed to look numbers between 1 and 8. So x equals 0 doesn't even apply because we're not on the interval. This one, I'm going to add 16 over x squared to the other side, set that equal to 1. That means that 16 is equal to x squared, and 4, or negative 4, is equal to x. So these are my 2 critical numbers, but again, negative 4 was not on my interval from 1 to 8. So I really just have a critical number at x equals 4. Now, from here, you have some options that you do need to verify with calculus. You could set up a number line for slope prime. You could look between 1 and 8, plot 4, and you find that this does, in fact, come back negative positive, in which case 4 is acting as a minimum. You could also take the second derivative, I'll do that over here, m double prime, the derivative of 1 is 0, derivative of 0 is 0, this becomes 32x to the negative third, and when you take m double prime specifically at your critical number of 4, you end up with a number that is greater than 0, which means your graph was concave up, and you have in fact a minimum at 4. So we have 4 as a candidate for the minimum. I just need to double check those pesky endpoints. So I've set up all of my candidates, right? This is a candidates test. From here then, I'm going to take those candidates and I'm going to sub into my slope equation. And if you remember, my slope equation was nicely written as x minus 1 plus 16 over x. That was my best, kind of neatest slope. So when I sub 1 into there, 1 minus 1 is 0, plus 16 over 1 is 16. When I substitute 4 in, I get 4 minus 1, which is 3, plus 16 over 4, which is 4. 3 plus 4 is 7. When I sub 8 in, I get 8 minus 1 is 7, plus 16 over 8, which is 2. 7 plus 2 is 9. So from there, I doubly confirmed that this critical number, even when it's compared with its endpoints, ends up being where the minimum slope exists. All right, next one, the free response box. So this figure represents a square sheet of cardboard with a length of 40 by 40. So we're going to have 40 inches along here and 40 inches along here. And that's the full side of this piece of cardboard. Then we're going to cut out the parts that are not shaded in. So the shaded part is what remains. 4 squares with side length x and 2 rectangular regions are discarded from the cardboard. Well, let's think about this. If this is x and this is x, this is also going to have to be x. And then we could call these y's if that helps us, right? Because those are going to be the same in size when you fold the box up and around. So we have an x up here, right? So we are trying to find the size of the square x, that's our goal, that will result in the maximum possible volume. We were told that volume equals length times width times height. Our goal then is to figure out, if I want to take the derivative of that volume, I need to get in terms of a single variable. So let's just go piece by piece. I'm going to have the length of this box, right? When it's all said and done and folded up, the length of this green part of the box is going to be 40 inches minus the 2 x's that I cut out, because I would have removed 1x, 2x. The width of this box is going to be this part right here. Okay, well, the width of that box then is just a y value. We'll deal with that in a second. And then the height of the box is going to be when I fold the box up. How tall is it? That's going to be represented by these little kind of wings being folded up. And so I end up with a height of x, and this represents my volume. You might be like, well, wait a second. You still are dependent on more than just a single variable, and I agree with you. So let's think about how I can replace this y value. Okay, I need a helper equation. Well, I know that this whole thing started out as 40. So 40 is equal to 2x plus 2y. Great, lovely. This is my helper to help me solve for y. So I'm going to subtract 2x, and I'm going to divide by 2. So I end up with 20 minus x is equal to y. And this also makes sense if you think about the fact that when you fold your box up, you're going to have half 20 of the paper left to work with as one of your dimensions. All right, from here then, I could take the derivative and find the maximum volume, but I want to do a little distributing first to get me to a polynomial to take the derivative. So volume equals 40 times 20, it's going to be 800 minus 40x minus 40x plus 2x squared, all times x, which means my volume is 800x minus, this will be 80x squared plus 2x cubed. So make sure you can get there, okay? That's our volume equation. The next thing that I want to do is I want to take the derivative. So v prime, because I'm trying to maximize that, volume is going to be 800 minus 160x plus 6x squared. Okay, now I don't have a calculator, so this is a little bit frustrating, but I'm going to set this equal to 0. I'm also going to consider where this derivative may have been undefined. And the thing is, it won't be undefined because it's just a nice polynomial. Okay, Well, to solve this, I could do some factoring, and this one actually does factor. Or you could also use the quadratic formula. Either one, totally up to you. No matter what, though, I'm going to make my numbers a little bit smaller by dividing all of this by 2. And I can do that because 0 divided by 2 is just 0. This then becomes 400 minus 80x plus 3x squared. I'm then going to write this in standard form so that I could try to factor this if I wanted to. And this one, some of you are really good at factoring, and you can say, okay, well, this has to be 3x, and this has to be x, and then I know I'm going to need one that's positive, one that's negative, or sorry, 2 that are both negative because I have to get to negative 80, and I can just go from there. Some of you might take the route of splitting the middle term, where you're looking for 2 numbers, ones that multiply to 1200 and add to negative 80. Okay, that's one way you could go. But the way that we did in class, and the way that I would encourage also, if you're not so strong on your factoring, is the quadratic formula. So x equals opposite b plus or minus square root b squared minus 4ac all over 2a. You might be like, wow, that's a lot of big numbers, but let's go step by step. So this will all be 80 plus or minus. Negative 80 squared is the same thing as just thinking about 8 squared, right, which is 64. And then we've got the 2 zeros because the square, minus 4 times 3 is 12, times 4 is 48. So this is minus 4,800 all over 6. X is going to be equal to 80 plus or minus the square root of 1600 all over 6, which means 80 plus or minus the square root of 1600 is going to be 40 because the square root of 1600 is a 4 and a 10 all over 6. So I get x equals 80 plus 40 over 6, and I get x equals 80 minus 40 over 6. This ends up being 120 over 6 for 20. This ends up being just 40 over 6, which could also be 20 over 3. Next thing that I need to do is I need to figure out which one of these actually is the maximum. So I can do a number line, v prime. I can only look between 0 and 20 because that's how much paper I have. I would run out otherwise. And I do find out that this is a change from positive to negative. So 20/3 ends up being the x value I need for a maximum. The other option would be to use the second derivative. So my derivative was here, so I could take the second derivative, 6x minus 80. When I sub in 20/3, I end up with 40 minus 80, which is a negative number. So the second derivative, the double prime at 20/3 ends up being less than 0, which means my graph was concave down, and there is, in fact, a maximum. So some of you just missed some justification steps, okay? You found the 20/3 and you knew this had to be your answer, but you need to actually show it either in a second derivative test or in a first derivative number line test, either one. So we can conclude there will be a maximum value when x equals 20/3. Okay, and it doesn't ask us to find y, it doesn't ask us for the dimensions, it doesn't ask us for the volume. The question just says, what is the size of the square that we need to cut out? So we can stop there at 20/3. Did I include my inches? No, I did not. Inches. Make sure we have units. Okay, so again, start the primary equation, create some sort of a helper, sub in the helper, take the derivative, find the critical numbers, and then use calculus to justify your critical numbers.